Hello and welcome to our virtual open day. My name is Darren and I'm going to spend a few minutes trying to give you a bit of an overview of some of the design capabilities and design content that's on our mechanical engineering degree programme within the WolfsonSchool here at Loughborough University. As I'm sure you're aware, CAD stands for Computer Aided Design and has been around now for a number of years. This is a natural evolution from manual drafting, where we used to produce these engineering drawings by hand. So what we try and get across to students in the first year isn't just the ability to create the CAD models, although that is important, but it's to do it in a particular way that allows them to be easily edited. Because good CAD modelling is a skill, and if you do things the wrong way, then more often than not you waste a lot of time trying to correct those mistakes. Okay, there's lots of different CAD systems out there, and you may have used some of these already. If you're interested in having a play around before you come to university, I recommend downloading Google SketchUp because it's completely free for you to use. Within the WolfsonSchool, we use a piece of software called NX, and this is owned by Siemens. Normally when I speak to students, they've never heard of NX before coming to university, and that's perfectly normal at this stage. However, whilst you may not have heard of the software itself, I'm sure you'll have heard of many of these companies that are household names. All of these use NX as their primary CAD system. So Siemens, as you'd expect, because they own the software, but the likes of JCB and Dyson and Rolls-Royce use this on a daily basis to create all of their products. Okay, there's one noticeable absentee on there, and that's because they're a little bit twitchy about anybody using their logo. And so this is the closest I could get to it. So all of your iPads and your iPhones have also been designed using NX. Okay, so this is a really industrial piece of kit that we're going to teach you guys how to use. If we look at the content of the course from the first year, so this is primarily in the first semester, so pretty much between October and January, then you can see we start off right at the beginning trying to create some very basic sketches to allow us to create our 3D parts. And we build up complexity as we go through the course, trying to create more sophisticated CAD models and then how to generate the engineering drawings automatically from them. So as well as the engineering drawings for the individual components, we then learn how to bring those components together into an assembly and then generate the assembly drawings. And that's pretty much the end of that first year module. So I often get asked, why do we learn CAD? And what I'm trying to get across to you on this slide is that although in the first year what we're interested in is this red box here, so creating a good 3D CAD model and then using it to generate our 2D engineering drawings, throughout the rest of your degree program you're going to learn a lot of different topics, and many of them will rely on you starting with a good 3D CAD model. Okay, so whether that be stress analysis or computational fluid dynamics or some 3D printing, that 3D CAD model is fundamental. I'd like to quickly show you some examples from some of the remaining years of the degree programme. So we're going to start off with one from the second year, and this is where students build on those skills from the first year, starting off with a 2D sketch and then converting it into a 3D CAD model. And then we actually change application, and we can then move into our simulation world where we simulate what the material is made from, simulate how this thing is physically loaded and constrained, and then we can actually run some analysis, and that's what we're seeing here. So we've got lots of simultaneous equations being solved at the same time here, so we've got some matrix multiplication running in the background, and then we can actually see how this thing is going to behave. So we can see how much deflection there is. So maybe we need to stiffen the design up and reduce that deflection. We can also see the stress analysis, so we can see if we're going to exceed the material properties and if we need to redesign from that strength point of view. Okay, so this is fundamental to a mechanical engineer. More importantly though, this is all iterative, so we can go back into our design and we can make some changes and propagate those changes through, because all of these files are actually linked together within the CAE system. So here you can see we're adding a simple pocket, we're making the design lighter, and we're going to see how that affects the analysis. So all we need to do is propagate that change through the various files and rerun the analysis. So we can get updated deflection and stress data, see whether we've improved our design, and we can iterate again and again. And we can update all of our outputs as well. So if we've got drawings associated with this file or even some manufacturing data, we can just quickly run an update and generate some new CNC code for our 3-axis milling machine. If we go back into the assemblies, you can actually see that if we built our assembly correctly, then we can animate them as well. We can conduct a motion simulation and we can see how these parts fit together. Do we need to redesign anything? Is anything going to lock up? And we can actually link this back to the stress analysis and actually see all the dynamic loads and stresses. We've got another assembly example here where we can actually show how the parts would come apart, what order they would need to be disassembled in. This is really useful from a maintenance point of view. Can you actually remove the parts you need to service the product? We can also link our parameters together throughout an assembly. So you can see here just quickly changing the number of bolts, and all the components and any associated files also change. I've got a quick example of some surface modelling and some surface analysis that we can do to ensure that our surfaces are manufacturable. So you can see the reflection plots here that just help identify any imperfections that we can design out of the product. Here we've got a more advanced example of computer-aided manufacture from a third-year module, and you can see that we can change the tool shape and size, we can change how it actually moves across the model, and then we can simulate it to ensure that our tool paths are safe before we actually send this to the 3-axis milling machine. So that brings us to the end of the presentation. Thank you very much for listening. I hope this has been of interest to you, and hopefully we can see you at Loughborough at some point in the future. Thank you.